All right, nerds. Today we're going to finish up Unit 3.8. We're just going to be graphing more tangent stuff. If I say tangent wave by accident, I'm sorry. If I say midline or amplitude by accident, I'm sorry, because none of these things are true descriptors of tangent. Remember, tangent is literally just some function. It does not have a midline. It does, however, have a horizontal line that runs through the dead middle of the graph. We'll just say it's the line that goes through the inflection points. And it doesn't have an amplitude. It simply has vertical dilations. Okay? But if I say those things, I'm sorry. It is what it is. We're just going to be doing more tangent graphs with transformations, and at the very end, we'll write an equation of a tangent function from the graph. So literally, if you know the shape of tangent and you know where it quote-unquote starts and you know transformations, all of this is very easy. Cool beans? Cool beans. Awesome. Let's jump right into it. Got us a couple transformations here. We have a vertical shift of -1 units. Remember, we're not going to be saying up, down, left, and right anymore. We're just going to say positive and negative shifting. So this is a vertical shift of -1 units. That means down 1. So that horizontal line where we would have found all of our inflection points has been shifted down 1 from the x-axis. Let's go ahead and put that here. We do have a vertical dilation. The phone would ring right when I'm trying to teach. All right, phone conversation's over. Back to it. All right, guys, so I think I said right before I had to pause the video, yes, we have a vertical dilation of factor 2. What that means is when we used to go up 1 and down 1 to our 1 and -1, you know, between the inflection point and the asymptote, now we're going to go up 2 and down 2. That's all that means. So let's decide on our shape. I see no reflections, so our tangent graph will go left, down, and right up like we would expect it to. And our tangent graphs are always going to quote-unquote start at an inflection point, that one little dot I put right there. And that's going to happen at what makes the inside equal 0. So what makes the inside of this equal 0? Come on, guys, you can just say it. 0, good. All right, so we can see that we're going to start at 0, at x equals 0. We're going to have an inflection point at x equals 0, so we have to put that on our green horizontal line. That'll be right here. Awesome. Now all we need is our period length to figure out where the next inflection point goes, and we're ready to rock and roll. The period is going to be pi over b, because tangent, the parent tangent function, has a period of 1 pi. Remember, it repeats itself after quadrant 2. So we do pi over b, but the only number in front of our x is a 1, which means our period length is pi. So from this inflection point, I can go pi to the right and pi to the left to find my next inflection point. Pi to the right, pi to the left. That'll do it. Now between all of your inflection points is where you're going to find your vertical asymptotes, halfway in between them. That means I'm going to have a vertical asymptote right here, and then I'll have another vertical asymptote every pi to the left and pi to the right, because the asymptotes repeat themselves every period, just like the inflection points do. So we could see that every 2 marks is a pi. I said go pi to the right and pi to the left, didn't I? Oh, I said that right. I'll be okay. Every 2 marks is a half a pi. So I have to go 4 marks to get a full pi. 1, 2, 3, 4, right there. 1/2 plus 1 is 3.5. And do the same thing going left. 1/2 minus 1 is -1/2. Minus another 1 is -3/2. There it is. And then, like I said, this is going to, instead of going up 1, down 1 at the marks that are halfway between our inflection point and our asymptote, we're going to go up 2, down 2. So we said right up, left down, and we're going to repeat that pattern in all 3 zones, and then connect our dots, and we're ready to rock and roll. There it is. Ta-da! Not too bad. Yes, ma'am.
So the number of, it's just how much
Well, so remember in the parent tangent function at pi over 4, we are at a positive 1 because that's a 45, 45, 90 triangle. So a vertical dilation would just multiply our y values by whatever number's on front. So since it's supposed to be a 1, whatever number goes on front, it tells you literally go halfway between your inflection and your asymptote, and that's how far up you go and how far down you go. It doesn't do anything to the x values, no. Because that point is always going to be found halfway between the inflection point and the asymptote. Okay. Yeah, I mean, in this one, since this one has no horizontal dilations, we can actually say in quadrant 1, our 45, 45, 90 triangle would have been at pi over 4, which is halfway between 0 and pi over 2. And instead of saying up 1 from there, because tangent to 45 is 1, we have to go tangent of 45 is 1, times 2, so we got to go up 2. That's why. Okay. Now this one, again, I see no reflections. No reflections means the overall shape is the same. Left down, right up from our inflection point. Left down, right up, just like that. Of course, it's going to be up and down 3 from our line where our inflection points are found. And since there's no vertical shifting out here, that line of the inflection points is the x-axis. So we're going to be going to positive 3 and negative 3 for our 45, 45, 90 triangles. You know, halfway between the inflection point and the asymptote. No phase shifting. So just like this one, when there's no phase shifting, we're going to start at x equals 0, quote unquote. And I'm going to throw that on there real quick. There's that line of inflection points starting at x equals 0. So we got an inflection point right there. Now what we need to do is figure out what the period length is so we know how far to go left and right to find the next inflection point. Period is pi over b. And your b value is 1/2. Two pi. So go left 2 pi, go right 2 pi, and that is where you find your next inflection points. That's actually really far away. Halfway between our inflection points is where we can find our asymptotes. Halfway between 0 and 2 is 1. So 1 pi. And just like our inflection points, our asymptotes are going to repeat themselves once every period as well. So from negative pi to positive pi, yes, that is 2 pi. So just, holding on to that knowledge. Lastly, our up and down 3 from that line that goes through the inflection points. So it's right up, left down. So right up 3, left down 3. Just like that. This is a very steep tangent graph. Vertical dilation factor 3. But I'm hoping that you're thinking that this is pretty darn easy. Fingers crossed, you think it's easy. All right. Questions, comments, concerns? Or are you ready to start phase shifting and things like that? Phase shifting and reflecting. We ready for all the transformations? Boom. Okay, no vertical shifting. So the line where we find our inflection points is the x-axis. We do have a reflection. That's going to change the shape of the tangent wave. Oop, crap, said it. See, not supposed to say tangent wave, tangent graph. This will be left, up, right, down. How far up and down when we're at that pi over 4 region? 2 up and 2 down from our line that cuts through all of the inflection points. What makes the inside equal 0 for this one? Lots of people can say it, would make me happy. Negative pi over 2 makes the inside equal 0. That means we will find that first inflection point on that green dotted line at x equals negative pi over 2. Might as well throw it on there. Ba-doop, like that. Now, the period length. Supposed to be pi over b. Our b value is 1, the number in front of x. So pi to the right and pi to the left of this number right here is where we're going to find our other inflection points. Pi to the right, negative 1/2 plus 1 is 1/2. And 1/2 plus 1 is 1.5. Or you can just count the tick marks. 1, 2, 3, 4 to the right, 4 to the right, 4 to the left. Like that. Halfway between all those blue dots is where I'm going to find my vertical asymptotes, or vertical, or infinite discontinuities, let's say. That. And we're going to go left up to, right down to, from all of our inflection points, halfway between our inflection points and our asymptotes. So left up to, right down to. Make sure you are always watching the scale. You know, it just so happens that my y values were going by 1s, but they didn't have to. Just pay attention to the scale. Don't just count tick marks, please. There we go. Oops, missed a dot. Like that. Yeah.
When you're phase shifting tangents, does the sign on the pi over 2 matter? Does it be the same for
Well, okay, so the reason why for this example, why it didn't matter, this could have said plus pi over 2 or minus pi over 2, was because there was no horizontal dilation. So your question actually, it depends on the period length. So for example, if the period length was pi, like this one is, and this said shift by pi over 4.
Yeah, I know pi over 4.
Right, well that's because the period length is pi. So if the period length, how about this? If the phase shift is exactly half of a period length, then the plus or the minus, it wouldn't make a difference to the graph, it would be the same. But that's a very special case where the phase shift is exactly half the size of the period length. Well, this one we can't graph it the way it stands. So you guys had questions like this on your test that you took a couple days ago where the argument of the trigonometry was not factored. You need to factor it before you attempt to graph. Otherwise, you're not going to know what the appropriate phase shift is, because this looks like shift pi, but it's not shift pi. You have to factor out the 2, which is a form of division. So for this one, our period length is not going to be pi. Therefore, no, it won't be the same for this one. This one's period length will be pi over 2. What that means is, since my period length is pi over 2 and my phase shift was pi over 2, I could have gotten away with not shifting this at all. I didn't have to write this as a shifted equation. It could have been written as just 2x, because the phase shift is exactly the same size as the period length. But we're still going to graph it the way it stands. That way we get the practice. Cool beans? Cool beans. Alrighty. What do we see? We see no reflections. We have our standard left down, right up figure from the inflection point. The inflection points are all going to be found on the line y equals 2. Positive 2, right? Yes. We're going to start at what makes the inside equal 0, which is going to be positive pi over 2. We know we have an inflection point at pi over 2. Now this thing's period is actually kind of short. Is it this one I'm thinking of, or is it a later one? Is it this one? Yeah. Is this, yeah, but is this the one that has like a whole bunch? We'll see. And the period length is supposed to be pi over b. Our b is 2, so we have a period length of pi over 2. Holy crud. That means our next inflection point is pi over 2 to the left and pi over 2 to the right. Remarkably small period length. We're not going to go nuts. How about we graph a handful of them and then just say so on and so forth? You guys comfortable with that idea? Halfway between all of those inflection points, I'm going to find my vertical asymptotes. And on this scale, they are literally one tick mark away from it's hard to draw and talk at the same time. One tick mark away from the inflection points. So I can put one more vertical asymptote right here. So as far as our up 3 and down 3s are concerned, we actually need to throw some extra tick marks on our x-axis. At all of the, let's see, if this is a pi over 2 cut into fourths, each of these is a pi over 8. So pi over 8, 2 pi over 8, 3 pi over 8, 4 pi over 8. Itty bitty. So left down 2, right up 2, because the y-axis does count by 2s. Ones, excuse me, sorry. I heard somebody in the room go, Again, you know, talking, writing, and thinking about what you're going to do and say next all at the same time. It's like playing mental drum set. There we go. I got all parts of my brain doing something different at once. Oh, crap. What'd I do wrong now? It's in pen. I can't even fix it. 5, not 4. Poop. I used not an amplitude, but a vertical stretch of factor 2, didn't I? Eek. Well, it's in pen and I can't fix it, so I'm going to do this. There we go. Now it works. Sorry, guys. Turns out I can count, but I can't read. You know, it's just not a McCutcheon lesson unless there's some mistakes, you know. It can't be perfect. I don't want you guys getting any, like, false thoughts about me. Excuses. All right. Next. It's not bad, right? You guys are cool? It's pretty easy. I think the hardest part is just, do you know the shape? That's the hardest part. Boop. All right, so this is using a graphing calculator, but we're going to do it without a graphing calculator because, well, you don't need a graphing calculator. But I'm not going to answer these questions first. First thing I'm going to do is what I suggest all of you do when you're taking your test this next time when we end the unit is draw the pictures, please. Draw the pictures. When looking at your guys' tests, I saw a lot of you whose grades probably would have been higher had you taken the time to draw some pictures. I don't do trig, graphing, or evaluating without pictures. I always draw something. So I'm going to graph this first, and then I'll come back and I'll answer these questions. Because I can't see this graph in my head, and I don't have this dumb stuff memorized. No reason to fill brain space with that kind of stuff. That's my opinion, at least. Alrighty, what do I see? I see no reflections because there's no negative signs. That means the shape of our tangent function is exactly what we expect, a right up, left down situation from the inflection point. And since I've already said the inflection points, let's talk about where we're going to find them. We're going to find them on the line y equals -2. What else? I'm trying to squeeze it all in here. What else? Well, I would go for the period length next, yeah? Or where we start at. What makes the inside equal 0? 0 again. So this one has no phase shifting. That means the first inflection point will be found at x equals 0 on that green dotted line. Might as well throw that on there. Boop, there it is. Awesome. Next is the period length, at least for my process, right here. So we say the period length is supposed to be pi over b, but your b value is 1/4. And when you divide by 1/4, it's the same as multiplying by 4. The period length is 4 pi. That's a huge period length. Now, this graph, though, is not gridded. We get to choose the scale. I say we go by 4 pi's at first. So I'm going to do this. I'm going to say there's a 4 pi. And then another 4 pi puts me at 8 pi. That feels good. I'll go left 4 pi, doing my best to make that even. There it is. One last thing. The scale on the y-axis is clearly going by ones. I need to go up 3 and down 3. There. So from 1 to -5. Those are going to be my critical y values, if you want to talk about it that way. Cool. So we know we have a period length of 4 pi. That means I'm going to find an inflection point at every 4 pi to the right and 4 pi to the left. So I've got one there, I've got one there, there, and there. Now halfway between all of those is where I'm going to find my vertical asymptotes. So those are going to be at 2 pi, 6 pi, -2 pi, -6 pi. Let's go ahead and mark that 2 pi. And lastly, at every single pi, that's where I'm going to do the up and down 3. And since this is my shape, it's going to be left down 3, right up 3. Left down 3, right up 3. And just do that a few times. Bless you. I'm going to get 3 full periods on there and just call it a day after that. That's good enough. That's more than enough graph in order to answer the rest of this stuff. The first 2 questions, well, I guess it's 1 question, but the first 2 pieces of information it's asking for are the left asymptote and the right asymptote. I can only imagine that we're talking about from the starting quote-unquote x, if you wanted to do it that way. So what we say, that's at -pi and then at, no, excuse me, -2 pi and at +2 pi. Is that what we said? So the left asymptote is going to happen at x equals -2 pi. And the right asymptote is going to be at x equals +2 pi. But you know that the asymptotes are going to repeat themselves every full period. So we could have just said, where are the asymptotes? And we could have said that they are at 2 pi plus 4 pi in, because that would include the positive and negative versions of that. But that's not the way it's worded, so we'll just answer it that way. Transformations, well, that's good old, unit 1 stuff. Vertical dilation, factor 3. Horizontal dilation, factor 4. Remember, horizontal inside opposite, so it looks like we're dividing by 4. No, we're actually multiplying by 4. So we have a horizontal dilation of factor 4. And lastly, vertical shift, -2 units. We need to get away from saying up, down, left, right, and just use positive, negative. Vertical shift, negative, oops, forgot the T, -2 units. concavity. Boop. It doesn't matter that this tangent graph has been reflected. It's still concave up above that green dotted line and still concave down below that green dotted line. So how do we describe all of these concave up zones? Well, all these concave up zones go from an inflection point to the right to an asymptote. So begin at an inflection point and approach but never actually get to the asymptote. I'm describing up first, so I'll go ahead and write that one first since I started saying it. We are concave up. You know, I haven't written in orange yet today. I'm going to move over to the orange pen. We are concave up from 0 to 2 pi. But that zone is going to repeat itself every period. And the period length is 4 pi. And of course, this is going to be for our n is an integer. Yes, sir?
Again, shouldn't it be in bracket?
Not for concavity.
Always concave.
Yep, concavity doesn't use brackets because this tangent function is always increasing. And even then, we wouldn't use brackets because it doesn't exist at its asymptotes. Concave down is the left side of one of these things, to the left of its inflection point. So from the asymptote at negative pi over 2, but that's obviously going to repeat itself every period, and coming up to the inflection point at x equals 0, but again, repeating itself. Oh, I didn't mean to put the minus. It's not wrong to put the minus, but it's redundant. Because when you say n is an integer, that means positive and negative. So we'll just, nothing happened. You don't see that. It's not necessary. It's not wrong, but it's redundant. Where are our inflection points? Well, let's see. I've got one at 0, then 4 pi, then 8 pi, but that looks like the multiples of 4 pi to me. So it's going to occur at every coordinate of 4 pi in, comma, negative 2, because they all have the same y value. And all three of these are, for n is all the integers. That means positive and negative. So every multiple of 4 pi. It's not bad, is it? I honestly think memorizing all of those like formulas and stuff like that to fill this out and then graph is ignorant. Why? If you're going to have to graph anyway, why wouldn't you just graph it and then read your picture? I've memorized very little. For this next one, because it's the exact same kind of question, you guys cool with it if we just graph it and then move on to the back? Since it's all the same skill set? Hope you don't mind doing that. I want to get to the back. Make sure we have time for that. Alrighty, what do we see? What do we see? We see, a reflection. We already know then that the shape is backwards or upside down. It doesn't matter which way you describe that because tangent is an odd function. But it's going to look like that. Now, we could talk about where we start, quote unquote, at what makes the inside equal 0, negative pi. That's where we're going to have our first inflection point at x equals negative pi, but we might as well know the y value where that occurs. Boop, right there, positive 1. Inflection points are going to occur on the line y equals positive 1. And before I go throwing a negative pi on there, I want to decide my x scale, which I'm going to need the period length to help me do that. Pi over b, our b is 1/2, with a period length of 2 pi. So I'm going to begin at negative pi. I'm going to go left 2 pi and right 2 pi to find my next inflection point. So let's see. Let's say that's negative pi. And go to the right 2 pi. So I'm just going to have mine go from negative 2 pi to positive 2 pi. That's going to be enough. We know the First inflection point happens at x equals negative pi, so that's going to be right here on my green dotted line. If I go 2 pi to the right, I find my next inflection point. Halfway between my inflection points, vertical asymptotes. And the vertical asymptotes, just like the inflection points, repeat themselves every period length. So 2 pi left and 2 pi right. So the way that I've drawn this, I have just enough space to get 2 periods on there. I attempted to do to scale, but as you can see, my negative 2 pi went a little bit too far right, and my positive 2 pi went a little bit too far left and right. Oops. I did my best. Let's put our half marks on there. So those are going to be half pi's. So a pi over 2, 3 pi over 2, negative pi over 2, and negative 3 pi over 2. They're halves. And we know we're going to have to have this shape, and we're going to have to go up 2 and down 2 from the green dotted line. Up 2 and down 2 like that. So left up, right down. Left up, right down. I attempted to get my picture to scale, but failed miserably. That's it for that. I mean, if you wanted to take the time to list out where the asymptotes are, or the concavity, the transformations, you're welcome to, but we've done that. Transformations, I feel like we've beat the crap out of that dead horse. And we've been doing this a lot with the whole plus period length, where period length is an element of, where n is an element of integers. We've done that so many times. I would rather just move on with my life. Everybody's comfortable with that? Moving on with our lives? Yes? Okay. To the back. Numbers 1, 2, 3, 4 are just matching questions. I think it would be easiest to start with these two. And the reason why I say these two is because of the vertical shift. Graph B will have all of its inflection points happening at y equals negative 2. So is that picture 1, 2, 3, or 4? Yeah, picture 3 must be graph B, because that has all of its inflection points happening on the line y equals negative 2. And if we look back up to here to graph D, its inflection points are going to happen at y equals positive 1. Is that graph 1, 2, or 4? Clearly it is 4. All right. Skirt. As far as these two equations are concerned, one has a phase shift and one does not. So graph A has no phase shift. Which picture is that, 1 or 2? 2 has no phase shift, so that's A. Clearly this is C. Look how easy matching is when you understand the shape of tangent. Pretty darn easy, right? Cool. Next, arguably the most difficult skill, writing the equation of the tangent graph from its picture. Now, I don't know about A and D. I'm just going to mention what transformations we see based on looking at the picture. No AP question is going to say what's transformation A, what's transformation D, unless they say in that question this setup and then go, what's the value of A? But since we don't see that, I'm not going to do that. I'm just going to go, here's the transformations that we can view. First of all, you should be able to see the horizontal line where your inflection points occur. What y value is that? Positive 2. So at y equals positive 2, we clearly have a line for our inflection points. So let's say a vertical shift, but I'm not going to say that first. Because if I'm describing my transformations, the vertical transformations have to occur in PEMDAS order. I need to know what the multiplier on the front would be. First of all, do I have a reflection? No. That tells us that the number on the front of our tangent function is positive because there's no reflection. We just need to know what that value would be. Now, how do we identify that as the question? Here's the best way to estimate it. You know that your asymptotes are going to happen halfway between all of your inflection points. You can also look to see at which x value your graph starts to hug. Well, we got that right there. And then this one right here. So halfway between the blue dot and the red line is where I should have found the up and down number on the front of tangent. Halfway between this number and this number is this number. So I didn't even need to know what it was. I just counted tick marks. It's occurring right there. So if you had to estimate that value, it was supposed to go up 1, but it clearly didn't. 1/2 feels like a good estimate, yes. So if I had to guess or wager, I would say we have a vertical dilation of factor 1/2. Or you could just say there's a 1/2 on the front. If you want to do that, doesn't really matter. Let's just say 1/2 on front. And a +2 at the end, because it's been shifted up to a vertical shift of +2 units. The period length is just going to be from blue dot to blue dot or red line to red line, and they kind of made it a little bit of a pain in the butt because of where the dots are. So here's the hack for that. You ready? Just figure out the scale that they've used from 0 to pi. They used 1, 2, 3, 4 tick marks. So that means every tick mark is 1/4 of a pi over 4, right? So then just look at the number of tick marks between the blue dots or the number of tick marks between the red lines. Let's go blue dots. 1, 2, 3, 4. Oh, 4 tick marks. And since every tick mark was a pi over 4, our period length is pi. And you could confirm by saying this is -3 pi over 4. And the next one occurred at positive pi over 4. -3 pi over 4 plus pi, yes, that is positive pi over 4. -3/4 plus 1 is positive 1/4. So then what's the phase shift? Well, there's an infinite number of correct answers. Just pick one of them. Yeah, I would pick the one that's closest to 0 if it was me. So I would say that it was this one right there. I'd say that that is a shift, a horizontal shift of pi over 4 units. It says label the inflection points. Well, I mean, they're the blue dots. So I don't even know what to write there. So I'm not going to bother. Clearly, it's the blue dots. I mean, if you wanted to write them as a describe all of the inflection points, you could. You could do it like this. You could say, I'm going to start with the smallest one, pi over 4. When I say smallest, I mean closest to 0. You could say they're happening every pi over 4 plus a period length times n, comma, the y value is always 2. And this is where n is an integer. You could do it that way if you wanted to. That describes every inflection point, positive and negative. So the equation. Honestly, I feel like the hardest part about the equation now is determining what your b value would be. So let's just go ahead and determine b. Remember, period is supposed to be pi over b. So we have pi over b equals our period length of pi. Normally you'd have to cross multiply and simplify and all that stuff, but what does b equal? B is just 1 for this one. So we're not even going to need to write it. Let's get our ending equation. We have, I'm going to write it in black. We have f of x or y equals, who cares? Let's just do y equals. We know the number on front is positive because it had no reflections, and we already know it's a 1/2. So we've got a 1/2 tangent of, since b is 1, we are not going to put a number in front of x. And we said a shift of pi over 4 units, but we all know that means go to the right, so horizontal inside opposite. And the line where we find out all of our inflection points has been shifted up 2. That's why we wrote plus 2 at the end. That is the equation for this graph. One of many infinitely correct equations, just depending on your phase shifting. But I'd say that's the easiest one, the lowest hanging fruit. Do you have questions about it? Or are we all big old tangent nerds now? Silence. Okay, I'm going to take that as big old tangent nerds. Thank you. Oh, you are? Okay, good.